You're listening to a special AI-powered training session generated based on my original research and training documents. While the voices you are about to hear are AI-generated, the insights come directly from my verified material.
Welcome to the Epoch Zero Show. Today we are unpacking Module 1.3.2, Deep Learning Revolution, from 2012 to 2017. This period, it wasn't some single aha moment. No, it was more like a 5-year cascade, a series of foundational breakthroughs. Think of it like dominoes. Once the first one fell, it set off a chain reaction that built the entire world of AI we live in today.
So yeah, a chain reaction. You had these massive, once unsolvable problems in computer vision, in language, even in strategic reasoning, and they were just systematically dismantled. So let's unpack each of these pillars one by one.
All right, so our story kicks off in 2012. The stage is set at the ImageNet Large-Scale Visual Recognition Challenge. Now, you have to understand, at the time, this competition, it was the undisputed benchmark for computer vision. It was basically the Olympics for this field.
And then this small team from the University of Toronto, they show up with a model they called AlexNet. And, well, it didn't just win. It absolutely shattered the competition. We're talking a full 10.4 percentage point lead over the runner-up. I mean, a result that decisive, it just ended the era of traditional computer vision. Overnight. It was a total shock to the system. The old way was done.
So what was the winning formula? It was a perfect storm, really. First, you had a deep, 8-layer convolutional neural network. Second, they used the faster ReLU activation function, which was key to keeping training times from getting out of hand. Third, they used dropout regularization to stop the model from just, memorizing the data. But the real secret ingredient, this whole thing was powered by parallel processing on 2 off-the-shelf NVIDIA gaming GPUs. That combination, deep architecture, big data, and GPU compute, that became the blueprint. The hypothesis was proven right.
So, AlexNet proved one thing beyond a shadow of a doubt. Depth mattered. And just like that, the race was on. The big question became, how do we build networks that aren't just 8 layers deep, but dozens, maybe even hundreds of layers deep? But there was this one fundamental roadblock standing right in the way.
And that roadblock, it's called the vanishing gradient problem. It's kind of like that game of telephone. You whisper a message down a long line of people, and by the time it gets to the end, the message is either completely garbled or just gone. Well, in deep networks, the learning signal, the error signal, it would fade to nothing as it traveled backwards. The deepest layers, they just stopped learning. It put a hard cap on how deep anyone could build a network. Then, in 2015, some researchers at Microsoft came up with this really elegant and simple solution. They called it a residual network, or ResNet. The core idea? To create what they called skip connections. Think of them as architectural shortcuts, basically an express lane on a highway for the gradient. This let the learning signal just bypass the troublesome layers and flow totally unimpeded straight to the deepest parts of the network.
And the result? It was just staggering. I mean, previous models like VGGNet, they topped out around 19 layers. The very first ResNet was 152 layers deep. And just like that, the vanishing gradient problem was solved. That hard cap on depth was completely gone. Networks could now be, well, arbitrarily deep.
Now, while all this was happening in computer vision, you had these parallel revolutions brewing in totally different areas. Researchers weren't just teaching machines to see anymore. Now they were teaching them to understand the meaning of words and even to generate completely new data from scratch.
So in 2013, Google's Word2Vec came along and showed that you could map language into this high-dimensional vector space. And inside this space, semantic relationships just became simple math problems. You could literally do arithmetic with concepts. King minus man plus woman equals queen. This became the absolute foundation for modern NLP.
Then, in 2014, Ian Goodfellow introduces something called generative adversarial networks, or GANs. And the concept is just brilliant. You pit 2 neural networks against each other in a duel. You have a generator, think of it like an art forger, trying to create realistic fakes. And then you have a discriminator, that's the detective, trying to spot the fakes. Through this constant battle, the generator gets so good that its creations are indistinguishable from reality. This gave us our first truly photorealistic AI-generated images. A whole new capability was born, creation itself.
Okay, so the next grand challenge, it wasn't about perception. It was about something much more elusive. It was about strategy. And the ultimate test was the ancient game of Go.
Its complexity is just profound. It had long been considered this bastion of human intuition, a game, people thought, that could never be cracked by brute force.
I mean, the complexity of Go it's astronomical. There are more possible board positions than there are atoms in the known universe. So the kind of brute force calculation that beat Garry Kasparov in chess, that was completely off the table. A fundamentally different approach was needed. Period.
DeepMind's AlphaGo was this hybrid masterpiece. It combined two deep neural networks. One was a policy network, which acted like an intuition, predicting which moves were promising. The other was a value network, which judged the strength of any board position. And this was all fused with a powerful search algorithm to explore all the possibilities. First, it trained on millions of human games, and then it honed its skills by playing millions of games against itself. It was this perfect fusion of neural intuition and symbolic search.
So, March 2016, AlphaGo defeats the world champion Lee Sedol. In the pivotal moment, it came in the second game, move 37. It was a move so alien, so completely unexpected, that the human commentators were convinced it was a mistake, but they were wrong. It was a brilliant, deeply creative move that sealed the win. And in that moment, it became crystal clear. AlphaGo had mastered intuition.
Okay, let's take a step back and analyze this. Why was deep learning so wildly successful during this time? It really boils down to two core strategic principles that explain why it dominated.
The first one is something called end-to-end learning. See, before this period, engineers would spend months, sometimes years, manually handcrafting features from raw data. Deep learning just automated the entire process. The network learned the best features directly from raw pixels or from text. This completely removed a massive, expensive bottleneck from the development process.
And the second big principle? Transfer learning. The idea here is that you could take a huge model that was pre-trained on a general dataset like ImageNet, and then you could fine-tune it for a new, very specific task using just a tiny fraction of the data. You weren't starting from scratch every single time. And this is what made powerful AI truly accessible to everyone.
So by 2017, deep learning had pretty much conquered images. It had made these incredible leaps in strategic games. But language, especially the challenge of handling long, complex sequences of text, that remained a really stubborn final frontier.
You see, the dominant models of the time, things like LSTMs, they were recurrent. That means they processed text one word at a time, in sequence. This was just inherently slow, and it made it incredibly difficult for the model to make connections between words that were far apart in a long piece of text. The sequential processing itself, that was the bottleneck.
And then, researchers at Google proposed this truly radical idea. Just throw out recurrence altogether. Their landmark paper, Attention is All You Need, introduced the transformer architecture. And at its core was the attention mechanism. It was a way for the model to process every single word in a sentence at the exact same time, while weighing the importance of every other word. It was a total paradigm shift.
The impact was immediate, and it was total. Within just 18 months, transformer-based models like BERT and GPT had just smashed every single NLP benchmark. And within a couple of years, it became the default architecture, not just for language, but for vision, for biology, for pretty much every other domain out there.
The transformer really was the final critical piece of the puzzle from this era. This wasn't just some incremental improvement over the old models. No, it was a completely new way of processing sequential data at a massive scale. It was the universal architecture the entire field had been waiting for.
So from AlexNet's first spark, all the way to the Transformer's universal design, this incredible 5-year stretch gave us the fundamental toolkit that we still use today. For leaders in this field, the core technical risk, it's gone. The question is no longer if AI works. The strategic question, really the only question, is how to deploy it.